Probability is rarely a static measurement. It is a fluid environment that violently shifts the moment a new piece of evidence is introduced. Standard probability calculates the likelihood of an outcome by measuring a specific subset's area against an entire universal sample space. But the core axiom relies on a strict parameter. When we condition on event A, we dictate that it has absolutely occurred. Geometrically, everything outside event A is instantly discarded. Event A expands to become the new normalized universe, permanently changing the denominator for all subsequent probability measurements. Understanding this concept of the geometric reduced space is the necessary foundation for reverse engineering complex stochastic problems. We can translate this physical collapse directly into the standard algebraic notation used by statisticians. This expression defines the conditional probability of event B occurring, strictly given that event A has occurred. The numerator, the intersection of A and B, isolates the specific events that manage to occur within our newly established parameters. The denominator, the probability of event A, acts as the scaling factor. It divides the remaining probabilities to force our new, reduced space to equal a complete 100%. This simple algebraic fraction serves as the primary engine for all complex probabilistic inference frameworks. To test this formula in practice, we have to map a sequential chain of dependent variables. Consider a classic probability exercise, randomly selecting one of two specific urns, and then randomly selecting a colored ball from that chosen urn. This schematic is an event tree. It provides a visual framework to track these sequential decisions. The top node represents our unconditional start state, a split of choosing either urn I or urn 2. The secondary nodes map the conditional probability of drawing a specific outcome, such as a white ball, strictly given the specific urn we just selected. We can extract the multiplication rule by rearranging our earlier algebraic fraction to solve for the intersection. The probability of choosing urn I and a white ball equals the probability of choosing urn I multiplied by the conditional probability of drawing a white ball from it. On the event tree, this is applied geometrically. We multiply straight down a single path. 1/2 multiplied by 1/2 calculates a 1 in 4 overall probability for this specific sequence. Event trees perfectly map the multiplication rule. They physically link unconditional choices to their conditional outcomes. But analysis often demands that we solve a broader problem. How do we determine the overall chance of a specific end state occurring, regardless of the initial path taken? Finding the unconditional probability of a final outcome requires aggregating all mutually exclusive paths that lead to that specific result. Looking at this abstract structure, we can see that outcome B satisfies our condition at multiple terminal nodes. The law of total probability states that we can find the total likelihood of B through a simple algebraic summation of these specific intersections. By substituting the multiplication rule into this summation, we expand the equation to show every distinct conditional step required to reach the target outcome. This expanded equation is the ultimate denominator for complex probability inversions. It captures every possible reality that leads to an observed effect. This brings us to a primary objective of data science, reverse engineering causality. The inversion problem asks a specific question. If we observe a clear outcome, what is the exact probability it originated from one specific initial condition?
This document outlines Bayes' theorem, the defining tool for calculating probability inversions. The architecture of the formula is a direct synthesis of the previous two rules. Conceptually, the numerator utilizes the multiplication rule to represent the single specific causal path we are trying to test. The denominator utilizes the law of total probability to represent the entire universe of paths that could possibly lead to our observed effect. Bayes' rule is a proportional relationship. It calculates the rigid mathematical weight of one specific path against all possible realities. We can test these mathematical tools against our own cognitive biases by examining a high-stakes scenario, medical diagnostics. Assume a doctor is using a highly accurate diagnostic test to screen patients for a rare disease. We are given 3 strict inputs: a prior probability of a 1% disease prevalence in the population, a true positive accuracy rate of 95%, and a false positive error rate of just 0.5%. We pose the inversion question using Bayes logic. If a patient tests positive, what is the true probability they actually carry the disease? When we process these inputs through Bayes' theorem, the resulting calculation is 65.7%. Human intuition expects a 95% probability, strictly matching the test's high accuracy rating. The violent clash between that intuition and the mathematical reality of 65.7% is known as the base rate fallacy. Staring at algebraic manipulation often fails to build true intuition. To understand why the math works, we have to translate it into a more concrete physical framework. We can verify the Bayesian calculation visually through a frequency scaling technique known as a model population. We establish our baseline parameters by projecting these statistics onto a hypothetical population of exactly 100,000 individuals. We mapped the 1% disease prevalence rate onto the population first. This gives us a base rate of 1,000 people with the disease and 99,000 healthy individuals. Next, we apply the 95% true positive rate strictly to the diseased subpopulation. That results in exactly 950 positive tests. Then we apply the 0.5% false positive rate strictly to the healthy subpopulation. Because that base pool is so massive, 0.5% yields 495 positive tests. We now redefine our probability space. We observed a positive test, so everything without a positive test is discarded. Our new universe consists entirely of the 1,445 individuals who tested positive. To find the final probability, we look at the diseased fraction of this new reduced group. 950 true positives divided by 1,445 total positives equals exactly 65.7%. Frequency-based scaling visually enforces the reduced space axiom. It mathematically prevents base rate neglect by forcing us to calculate the absolute volumes of both populations. Pulling back from the medical diagnostic scenario, we can see the broader objective of advanced stochastic analysis. We have examined 3 isomorphic frameworks to map the same logic: standard algebraic formulas, geometric event trees, and frequency-based model populations. Mastering statistical inference requires the ability to translate fluidly between these 3 systems to verify your logic and expose structural biases. The foundational geometry remains constant. Every piece of new evidence forces the absolute boundaries of the probability space to shrink. By anchoring Bayesian logic inside these rigid geometric and algebraic frameworks, an analyst can confidently reverse engineer the causality of any system.
Knowledge is power, boy. Like, subscribe, and prepare for the next battle.